All right, hello. Today, let's see, we're doing number 27, Unit 2, Big Idea 1, Lesson 2. All right, Big Idea 1, Lesson 2, which I think will be number 27 when we get there. All right, the big idea. The big idea for this, there's going to be four big ideas in the Unit 2. The first big idea is the rate of change distinguishes linear and exponential function families. Concerned because my mouse has decided to pause and not move. So let me get new batteries for this. All right, much better. My mouse is now moving. All right. The learning target. The learning target is, I can. I need to change it to I can. I can compare how arithmetic and geometric sequences grow, connecting these sequences to linear and exponential functions. All right. So by the end of this, hopefully you can compare how arithmetic and geometric sequences grow, connecting these sequences to linear and exponential functions. All right. Arithmetic sequences are like linear functions, and geometric sequences are like exponential functions. Okay. So let's look at this sequence here and see what you notice and answer the question below. All right. So maybe just pause right here and take a look at what we got. Pause me now. All right. So we see here Latoya. Latoya uses this sequence where each circle represents the number of thousands of bacteria in a petri dish each hour. How many bacteria will be in the petri dish in hour 5? Okay. So each of these dots represents 1,000 bacteria. So here's 1,000, 2,000 bacteria in hour 1. In hour 2, we've got 1, 2, 3, 4, 4,000 bacteria in hour 2. In hour 3, we've got 4 plus 4. That's 8,000 bacteria in hour 3. And then in hour 4, I got 4 plus 4 plus 4 plus 4. And that's 16. Another way to count this would be 4 times 4, right? 1, 2, 3, 4. 1, 2, 3, 4, right? 4 by 4, 16. How many bacteria? So 16,000 bacteria now. How many bacteria will be in the petri dish in hour 5? Maybe pause it, think about it, try to answer that question on your own. See what you can do. All right, you unpause me. If you got it, you got it. If you don't, let's think about this. We went from 2, 4, 8, 16. What is happening? What is happening? I started with 2. I went to 4, which is 2,000 more than 2. But then it went 2 fours, right? So it went up 2, up 4, up 8. So what's happening? It's doubling, right? 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. So how many bacteria will be there in hour 5? That will be 16 times 2. 16 times 2. You'll probably use your calculator, find that out, and it'll be thousands and thousands, right? This is 16,000, 16 times 2, and it'll be in thousands, all right? That's how we're going to answer that question right there. Ooh, but a more difficult question is how many bacteria will be in the petri dish in hour 10? In hour 10. Let me break out my calculator and let's see what we can come up with here. Let's see, there's going to be 2 in hour 1. Okay, 2. I'm going to times 2 to get hour 2, right? There's hour 2, 4,000 bacteria. In hour 3, I pressed enter again. Now it's 8. I press enter again. Now it's hour 4, hour 5, hour 6, hour 7, hour 8, hour 9, hour 10. I'm not going to press the button. You're going to figure it out. It'll be 512 times 2. All right? There's another way that we can do this. In math, sometimes we use what's called an exponential function to model something like this. For instance, 2 to the second power is the same thing as 2 times 2. All right? 2 to the third power would be 2 times 2 times 2. So 2 raised, this little caret raises it up, to the third power will be 8. 2 to the fourth power will be, what do you think? 2 to the fourth will be 16. So to find our 5, I could just 2 raised to the 5th power. Oh. And then 2 raised to the 9th power will be that 512 we saw, right? And then 2 to the 10th power, that'll give us the answer of how many bacteria will be in the dish at hour 10. All right, I'll leave you to your calculator on that one. All right, is it possible for the Petri dish to ever have exactly 2,000 bacteria? Explain your reasoning below. What do you think? Is it ever possible for the Petri dish to ever have exactly 2,000 bacteria? I'm going to let you just think about it. Think about it and try to answer the best you can with that one. Pause me, answer it, and then we'll continue. Okay. All right, here is the classwork today. All right, all of these are arithmetic sequences. All right, all of these are going to be arithmetic sequences. An arithmetic sequence is going to increase or decrease by the exact same amount each time. All right, so term 1 starts with 2. Term 2 has 4. Term 3 has 6. All right, so how is it changing? We're going to add or subtract the same amount each time. So 2 plus 2 is 4. 4 plus 2 is 6. Well, our job is to find the value of the next 4 terms. Well, if term 3 is 6, and if I add 2, I'll have 8. 8 plus 2 will be 10. 10 plus 2 will be 12, all right, and so on, all right? I'll let you finish that. You might want to pause me here. I'll make you go on and talk to B, about B. No, I'll let you do B. Let me talk about C. Let's see, I went from 24 to 18 to 12. So let me see what's going on here. Let me start with 24 and figure out what the difference is. 24 minus 18 is 6. All right, what's 18 minus 12? 18 minus 12 is 6. So what's happening here? What's happening here? It's minusing 6 each time, right? Let me test that theory. 24 minus 6, it's going to be 18. That's this number, right? 18 minus 6 is going to be 12, right? That's this number. So the next number here is going to be whatever 12 minus 6 is going to be, all right? 6. Well, the next number is going to be 6 minus 6. What's 6 minus 6? And then we're going to take that minus 6. Oh, that'll be a negative number, right? Right? 6 minus 6 is 0. And then minus 6 again will be negative 6. I'll have to minus 6 again to get the next number. All right, I'll leave that to you to finish that one up. Pause me and finish up B and D. All right? All right, you unpaused me. All right, here we go. Describe how these sequences are similar and how the sequences are different. So explain to me how these sequences here, what similarities do these 4 sequences have, and how are they different? Once you're done with that, you're going to describe how arithmetic sequences are similar to linear functions and how they are different from linear functions. All right. All right. Pause me. Answer those questions. All right, you've answered them. All right, let's go to geometric sequences. I'll do E and G and leave you the others. Let's see what's going on with E. In term 1, I've got 2 boxes. In term 2, I've got 4 boxes. In term 3, I've got 8 boxes. So what's happening? Right? 2 plus 2 is 4, that works. But then 4 plus 2 is 6. I'm not plussing by 2. I'm not plussing by 2. It's a geometric sequence, so I'm probably multiplying, right? Multiplying or dividing. 2 times 2 is 4. Okay, that works. 4 times 2 is 8. Oh, that works. That's what we're doing. We're multiplying by 2. What's 8 times 2? Would go here. And then take this number and times that by 2. It'll go there. All right, and keep doing that, and you'll have all the next 4 terms right there. Pause me if you need it. Otherwise, let me move on to G. I think you can handle this one. Figure out how this one is multiplying. This one is going down, so it's not multiplying, right? It's dividing by something. I got 24, 2, and 6. Maybe take a moment to think. What's going on? 24, 12, and 6. What is happening to these numbers? Well, 24 minus 12 is a difference of 12. But then 12 minus 12 would be 0. So it doesn't work. The whole minus thing doesn't work. We got to divide here. What about 24 divided by 2? 24 divided by 2 is 12. Oh, what's 12 divided by 2? 12 divided by 2. I divided 12 by 6. Whoops. 12 divided by 2, let me try that again, is 6, right? What's 6 divided by 2? Because that number is going to go right here. And then you're going to divide this number by 2. And then this number by 2. And keep going right there, all right? I'll leave you to it. Probably pause me here. Finish F, G, and H. Great. I'm unpaused. We're moving on. You're going to describe how the sequences are similar and how the sequences are different, right? How are these four sequences, these geometric sequences, how are they similar to each other, and how are they different from each other? All right. And then once you're done with there, describe how geometric sequences are similar to exponential functions and how they're different from exponential functions. All right. Just thinking about how are they similar, how are they different. Compare and contrast. Pause me here, get some words on this paper here. All right. All right. And we are now at the application and reflection portion. You're going to read the sentence and tell me whether it's always true, sometimes true, or never true, and explain why. A justification means explain. So, right here's the first one. A sequence that increases exponentially eventually exceeds a sequence that it increases linearly. So, think about that. Will a sequence that increases exponentially always eventually exceed a sequence that increases linearly? Sometimes or never? And explain why you chose the one you chose. All right, the next one is arithmetic sequences grow by equal amounts over equal intervals. Is that always true, sometimes true, or never true? And explain why. The third one is geometric sequences must grow by equal multiples over equal intervals. Is that always true, sometimes true, or never true? And the last one is for the same inputs, it is possible for all of the outputs of a linear function to be smaller than the outputs of a exponential function. Always true, sometimes true, or never true. Explain why, and then reflect how do arithmetic sequences grow differently from geometric sequences. And that's it. Then you're done. Okay? And then hopefully by the end of this, you can say that I can compare how arithmetic and geometric sequences grow, and I can connect these sequences to linear and exponential functions. All right? Very good. All right. Okay. I don't know what that's about. I got the weather report right there. Okay. I'm Mr. Solt, and I'll see you in class.